Let us continue the previous problem. So I have calculated the alpha value and beta value, reflection coefficient values at these junctions using these formulas. Now we'll apply that. So when a wave is incident with a magnitude 1 here, so we got here beta 1 is 0.2, therefore 1 into 0.2 will go like this. And we have calculated alpha, the transmission reflection coefficient, 1 into 1.2 is 1.2 will travel like this. So during this travel, it is multiplied with the attenuation constant 0.9. Therefore 1.2 into 0.9, 1.08 is the value reaching here. At this junction, so that is the junction 2, we have calculated again values, the reflection and refraction. So what 1.08 is the wave is entering here. It is reflected with minus 0.8. You have seen here is at this junction, the reflection is minus 0.8. Okay, so it is multiplied with minus 0.8, and the value coming from here is some value minus 0.864. That minus 0.8864 is multiplied with 0.9 attenuation. Then minus 0.778 is the value reaching here. At this position again, it is reflected. It is transmitted and it is again reflected. What is transmitted? Minus 0.778 into, we know this transmission coefficient 0.8. So that is minus 0.662 is the value coming here. What is reflected back? Minus 0.778 into, at this junction, when it is coming from this position, the reflection coefficient we got minus 0.2, beta 1 dash. So it is multiplied with minus 0.2, this is the value is coming here. So like this you can calculate the values. So if you take this junction, 1.08 is reflected and 1.08 into this 0.2 is transmitted at this junction. Because the junction J2, we have calculated the transmitted values multiplied with 0.2. So using these figures, you can calculate again. During this traveling, it is multiplied with 0.8 attenuation factor and 0.173 is the value reaching here. Again, at this junction, it will reflect and refract, transmit with different values. Like this, at every junction, when a wave with a value 1 is incident, it is subjected to reflections and refractions. The value at different junctions we can observe like this with the numerical values. Okay. So let us take the same thing what I have explained now. The values are given here, and this is the one, the previous picture. So we can take alpha beta values at junction 1, junction 2 and junction 3 like this, and we can further go for calculations. So reflection and transmission at T junction. Already you know about open circuit line, short circuit line, like that. If it is a T junction, we have come across these traveling waves in the previous semester. You can understand these points. When a wave incident with a voltage value E and I, if ER and IR in the reflected values, with a T junction, that means two lines are connected in parallel, they are connected to this line with impedances Z2, Z3. So this is the transmitted wave E2, I2, E3, I3 is the transmitted wave here. Then we can write what is the incident value E is equal to Z1 into I. What is the reflected value? Because it is opposite value. If it is open circuit, reflection is equal to incident. If there is something, it is not open circuit, the opposite to that value, minus Z1 into IR. Okay, minus value. So what is E2? Is equal to Z2 into I2. What is E3? I3 into Z. Therefore, these two are parallel. E2 is equal to E3, which is equal to transmitted voltage, which is equal to ER plus E, incident plus reflected voltage. And you know that IR plus I is equal to incident plus reflected current is equal to I2 plus I2. Sum of these. So T junction. So therefrom you can calculate for this T junction ER. You can obtain ER and ET from these expressions. ER is equal to this 1 by Z1 and these two are parallel by sum of all the impedances ET is equal to 2 times of this Z1 divided by sum of all the that's 1 by into ET. So we have to keep this one in mind and go for a discussion. So ER can be written like this: Z2, Z3 parallel. When a line is like this, junction J, Z2, Z3 are parallel. You can write like this: Z2, Z3 parallel minus Z1. Z2 minus Z1. Z2 is parallel combination of these two divided by parallel combination plus Z1 into E. What is the transmitted one? 2Z2. Z2 means here Z2 parallel to Z2. I'm talking if it is Z1, if it is Z2, think like that. In the previous one we have discussed, 2 into parallel combination divided by sum of all the into E. So let us see one or two problems on this. You will understand the application. So your overhead line A with a surge impedance 450 ohms is connected to 3 other lines. This line is connected to 3 other lines. There are 2 overhead lines B and C. Their surge impedances are given, each 600 ohms, and there is a cable in that D with a surge impedance 60 ohms at junction J. That means one line is connected to 3 lines. 2 are lines, one is cable. All are in parallel. A traveling wave of vertical front of magnitude 25 kilovolts, a very long tile like this, very long tile, a traveling wave, travels on A towards the junction J. Calculate the magnitude of the voltage, current waves which are transmitted, reflected when the surge reaches the junction J. Attenuation in the lines can be neglected. They have not given any attenuation quotient here. So you can calculate first what is the equivalent impedance of the 3 lines T junction. 3 lines are parallel, therefore 600, 600 and 60. All these are parallel combination. You have to calculate 50 ohms. Therefore, what is ET? You know the formula 2 into Z2 by Z1 plus Z2. Z2 means parallel combination of all this divided by Z1 plus Z2 into incident voltage 25 kilovolts. It is 5 kilovolts. This is the transmitted voltage. Out of 25 kV, 5 kV is the transmitted. What is the reflected voltage? Same for Z2 minus Z1 by Z1 plus Z2 into 25. It is minus 20. That means out of 25, 5 kV will be transmitted, 20 kV will be reflected back. So that is the traveling